Hi, everybody. Welcome to the third and final video of Joanne and her big sheet of pedigrees. This one is brachydactyly. I say that with confidence tonight because, oh, sorry. Oh, sorry. There it is. Okay, brachydactyly because I looked it up. And I knew, and this is how science is cool, with the dactyly at the end, I knew it had something to do with your fingers and toes because we talk about polydactyly. Well, brachydactyly is shorter than normal fingers and toes. Now you know. But we need to see what kind of inheritance pattern it is. So as always, I start at the bottom and I look for the pattern. The very first one and the easiest one to look for is all the people who have the traits. Okay, so all the dark colored ones, we need to see whether or not their parents have it. Because if the parents, at least one of them does, we know it's autosomal dominant. So start at the bottom. Okay, so 4, 5, and 6 here. Mom and dad had it. This generation, mom and dad had it. Okay, that's easy enough. And if we go all the way to the top, mom had it. These two here, mom had it. By the way, we haven't said it in class. That like that means twins. And her mom had it, so that's it. Parent, parent, parent. So every single occurrence, one or more of the parents. Okay, because you can see here, both parents had it. And for example, here, only one parent had it. That's enough. So this is autosomal dominant. And that, sorry, I'm going to sneeze again. That becomes important because it tells us how we should set up our letters, how we should set up our alleles. So since brachydactyly, feel free to say that a couple of times, this is a cool word, is dominant, I'm going to use capital B, brachydactyly, and little b, or normal. That's the first thing we know. You know what? I think I'm going to set up my 3 possible genotypes. So we can have 2 little b's because it's a recessive trait. That's going to be normal. Oh, sorry, move the camera over a little bit. I can have capital B, little b, which is the trait. We can't, sorry about those, the sneezes are trying to come. It's not a carrier. Like usually the heterozygous is a carrier, but this person is displaying the trait. So there's no questions about it. And just like the other choices, that is the unknown. We know they have the trait, but we don't have enough information based on the profile that we have to determine whether they are heterozygous or not. And my rule is you can never prove someone is heterozygous or homozygous dominant just from a pedigree. I think the only way you could do that is if there was some kind of a genetic test that you could do it. So that's my theory. All right. You know what? Let's be lazy. So since all of these people who are colored in have brachydactyly, everyone that's not doesn't have it. So everyone that's not is normal. So you may want to pause the video or fast forward it while I do this. Every single circle and square that is not colored in is 2 little b's. And away we go. Okay, you keep doing that. I'm going to pause the video. Okay. So I did some, and I'm sure you're just finishing up. All of these people are normal. And since it's a dominant trait, they don't have brachydactyly. And away we go. Every single one. And again, because it's an autosomal dominant, we could, oops, missed one. We can do that. So those are all the people that don't have the trait. If this doesn't make sense to you, think of it in terms of people with brown hair and blonde hair. Okay, we know blonde hair is recessive. All of these ones are all the blondes. There's only one possible genotype, so you can put it all in. Everybody else has brachydactyly, so we know they have at least one capital B gene. And I'm being lazy, like I have with all of these videos. I am not going to, I don't want to start thinking, because that sounds terrible. But really, I'm not going to start really digging into this pedigree until I've done as much as I can without any hard work. Oh, there we go. Okay. So now our trick is to figure out for all of the ones with the trait, what is the second choice? What is that second allele? Is it the lowercase? Is it the recessive? Or is it like, I don't know. So let's see. Let's start over here. This one looks pretty simple. If we look at individual number 10 and we go up to her parents, his parents, sorry, my bad, squares guy. We can see that mom has a trait, so that's where he got that from, but dad is normal. So the only possible gene dad can contribute is little b. So number 10 is heterozygous, we know for sure. And you know what? If we go up another generation, look at that. Mom is normal. So the only possible gene she can contribute, got it? Little b. And why not? Let's go one more. So we got this son here. If we look at his parents, once again, one of them is normal. So the only gene that they can contribute is little b. So we're positive of those. Now let's look at this middle one. It looked a little scary to me, so I'm a little afraid. But let's see. Starting at the bottom. Maybe. What I can tell is mom and dad here made this son, which means mom and dad up here must be heterozygous. We can, I don't want to use the word carrier, that like they're carrying the normal gene. So I'd rather just say they have the trait. But that's the only way that this baby is going to look like that. These ones, until we get the next generation, don't know. Because this capital B could have come from dad or mom, but I don't know what that second one is. Because it could be two big P's, that's a possibility, or it could be one of the lowercase b's. I don't know, so we're going to put a line. And this one unknown. So all of these siblings, it's the same idea. Yep, let's go up another generation. So for these two, let's look at their parents. Now, if we look at their children, I don't know about that one yet, but look, we have someone who has normal. And these two little B's must come from somewhere. So they must have come from dad and from mom. So we know these guys are heterozygous. So this row, number one daughter, not done yet. She got a capital B, so she has the trait. Now that could, again, come from mom. I keep doing that, from dad or from mom. Don't know. And we don't know what that second gene is. So if she got this from dad, she could have got this from mom, or she might have got that from mom. Don't know. And that's just the way it is. Not all pedigrees are going to be perfect. Not all pedigrees are going to allow you to know the genotype of every single person, but we can do a fairly good job. All right, so that part's done. All right, let's look at individual number 5. I want you to shout out at the TV or at your phone right now and tell me the genotype. Do we know this second one? Or are we doing this? Yeah, I know that you know. When we go up, dad is normal, so dad gave the normal gene. And you know what? Since we're this far up, let's look at mom. Grandma, great grandma, the female up here. If we look at her offspring, oh, there's an easy one. Actually, it was over there too. This daughter is normal, so she would have got one of those genes from dad, but she must have got the other one from mom. So she is heterozygous. We're almost there. Just got this last row to go through. Let's see. Normal, 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 normal. Here we go. We got these two gentlemen to deal with. Go up a generation, and we can see that dad is normal, so he is homozygous recessive. Little b for you too. Same theory. And then we've got these two. So we've got one of the twins and this girl over here. But if we trace back to the original parents, same story as this one, they are going to be heterozygous. This one I can also double check, because if this mom is heterozygous, that's the only way they're going to get that normal child there. And ta-da! That was an awful lot, but ta-da! We did it. We done did it. All right, one more. And maybe this one's, maybe, I don't know. Maybe it's going to be easier because it seems like there's not that many colored in ones. Maybe it's going to be easier for us. All right, so here we go. As always, we're going to start at the bottom. We're going to trace back generationally. So all of these kids, mom and dad had it, and mom and dad had it. But if we look at number 7 here, mom and dad don't have it. So right now we know it's autosomal recessive, or you could have looked, this one's just easier to circle. Right there. Also here. And remember, you only need one example in a genotype. So we know this is recessive. Again, because the parents don't have the trait and it shows up in the offspring. So the second question, once you decide it's recessive, is it X-linked or is it autosomal? And for that, you need to count. We've got 1, 2, 3, 4, 5 boys, 5 males. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 females. Well, with that ratio, I feel very confident in saying this is autosomal recessive. So remember, that just means this trait is found on the first 22 chromosomes. And possibly more importantly, we don't have to put X's and Y's on everything. It's only when it's a sex-linked trait do you need to worry about that. Okay. Now, this trait is for deaf mutism, and it's a recessive trait. So I'm going to choose N for normal hearing and little n for deaf mute. You could, again, you can use any letters that you want, but I certainly wouldn't use a capital D for normal hearing and a lowercase d for deaf mute. For me, that would just be confusing. So, you know, the other thing I'm going to do before I go further is, like we did on the last one, let's look at our genotypes. We can have that. We can have that. Those are our three choices all the time. Excuse me. Never, ever, 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 never, ever, ever, ever in my class are you going to get the homozygous dominant. You're not going to get two capitals on these. There's just never enough information. So this one, the person is a deaf mute. This one, they're normal. Now, is there another word we could add to that or use instead of it? Actually, after I wrote normal, I'm like, maybe that's not the right word. I'm going to put /carrier. And this one is basically unknown. I mean, we know they can hear, but we don't know whether they're a carrier or not. So I noticed up on the top, I just left it blank. So everybody that's colored in this one is a deaf mute, which means they get two little n's. And before we go further, I just want to show that this part here, where we figure out what the pattern is, really determines how our letters are going to work. Because on this one, on brachydactyly, where it was an autosomal dominant trait, we were able to go in and it was all the uncolored ones that didn't have the trait that we could put in right away. Well, this one, because it's a recessive trait, it's the people that have the trait that have the recessive ones. So I guess what I'm trying to say is up here, it was the blank ones or the uncolored ones that got the two recessive ones. Over here, it is the colored in ones because we're talking about a trait. So you can go ahead and do this. You can also pause the video if I'm writing too fast. Remember, I didn't tell you that. This is round 2 of this video because last night I forgot to turn the camera back on when I started doing it. So I'm fairly proficient at drawing a lot of little ends. There. And that's the only possible genotype we can have. I think for the most part, if you start by filling in where the recessive one goes, then the rest of it's not going to be too bad. Well, if all of those people have the trait, then everybody else has got normal hearing. So they're going to get a capital N, and then I will worry about what the second one is later. And that's an awful lot of capital N's. And as I said before, don't worry, I'm not going to give you something this big on the exam. So I'll tell you a secret. Normally what happens is You tend to either get it all right or all wrong. And I can figure that out by giving you this much. I don't need to give you the whole thing, but practice makes permanent. Okay, boom. We got all the people with normal hearing. Well, what are we going to do? Let's start over here. I don't know why. It just seems like a good plan. So these guys are all done. Let's look at individuals. So we're in generation 4, individuals 11 through 14. If we look at their parents, mom was deaf, which means the only gene she could contribute was the lowercase n. So we know boop, all these guys and gals are heterozygous. Now, if we look at dad, that's a good one because, see, mom, we know came from here. So the only choices she was going to have is 2 lowercase n's. Dad, don't know what that second gene is. If one of these children had been deaf, then we would know for sure he's heterozygous. But because nobody is, we don't know for sure. He could be homozygous dominant, but we don't know for sure. Okay, good. So this strand is done. Let's see now. Oh, let's go here. This feels like a similar situation, right? Dad is deaf, which means all of these children down here are going to get a lowercase n, so they're essentially going to be carriers. And same argument as before. We don't know what mom is. Clearly, mom contributed the capital N gene. But we don't know if there's a chance she could have had a lowercase, right? If we had an extra sibling on there that was colored in, then we would know for sure. So this one, a little bit unknown. Let's keep going. If we go up one more generation to generation 2, 4, and 5, to have this son, they must both been carriers. Now, let's finish off these siblings. They didn't have any kids. So they got a capital. Let's look at this daughter here. She got a normal gene, hearing gene from dad, or maybe from mom. Don't know, but she got one somewhere. But we don't know what that second gene is. She could have got normal from dad, normal from mom, or you could have got normal from dad, deaf from mom, or vice versa. So we don't know. And by the same logic, same with this sister. Where should we go? Oh, you know what? Let's do the grandparents, great-grandparents up here. If we take a look, I should have done it here. See, there's this daughter who is deaf, which means the parents must have been carriers. Let's look at these two. They kind of are standing out, waiting for something. If we look at the parents of this girl, they are heterozygous, but since she doesn't have any offspring, we don't know. And I'm going to say the same argument for the boy over here. We don't know if she had children and somebody ended up with the trait, then we know for sure she's heterozygous. But at this point, nope, don't know. All right, we are almost done. Done. All right, let's see what we got here. I'm going to do this part because it looks easier. These ones clearly came from there. Now, this capital N, lowercase 2 n's, that must have come from these parents. So we know they're heterozygous. This daughter We don't have information. So we're not sure about her. This son, same story. And this whole branch of the family. They could all be carriers, but we don't know. So blank, 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 blank. Ta-da! Congratulations. I'm just going to cover up that part. It's causing me grief. You have done it. You have, if you have sat through this and completed this, I hope you understand this. And if not, come see me and we can practice some more, or I can give you another copy of this, and maybe trying it on your own is going to be cool. All righty. Have a spectacular day. Happy genetics to y'all.